So, in the last lecture, I had stopped at Doppler broadening of carbon dioxide line and the carbon dioxide laser, and we had done a comparison of the line broadening of a few lines that we know of some famous lines like sodium line, helium line, all these things we had done a comparison. So, I had stopped at this broadening part. Now, here I want to just complete the line broadening as suppose you have two kinds of broadening. You know, there can be a natural broadening and then there can be Doppler broadening. So, it is a combination of two broadenings. And both of them have different line shape functions. So, what do you do when, how do you know the width, full width, half maximum of a combination of these two broadening lines? So, the shape of a composite emission line, so how would you do it, how would you do it mathematically? Suppose the shape of a composite emission line here, if one emission line is f1 omega and the other one is f2 omega, these characterize two different emission lines with the same central frequency omega 0. Okay. Now, what would be the total line shape function? And of course, these are broadening due to this simultaneous action. Okay. So, two broadening effects happening simultaneously, how would I find the composite line? The shape of the composite emission line is defined as follows: f omega is equal to integral of f1, which is one line delta, and f2 omega plus omega 0 minus delta, and you integrate out the delta part because we are not interested in that. Okay. And it goes from minus infinity to infinity. So, what you will be left with is a function which is a function of omega again. Okay. So, this is the way it is done. So, you can put in f1 maybe a Doppler broadened line, f2 could be a natural line broadening mechanism, and then the composite one will be this given by this formula. Suppose, just as an example, the addition of two Lorentzian lines, each of them with width gamma 1 and gamma 2. Okay. The composite emission line width is given as gamma 1 plus gamma 2. Okay. You have got to work it out, you know, you have got to do this full integral, just do it patiently and you will come to this conclusion. Okay. Here I am just giving you the results. Suppose you have gamma 1 and gamma 2, the final gamma is gamma 1 plus gamma 2 in case of addition of Lorentzian lines. Now, what happens in case of two Gaussian lines with width delta 1 and delta 2? That is given by delta is equal to root of delta 1 square plus delta 2 square. Okay, it is not just the ordinary addition like in a Lorentzian line, but it happens to be the root of the square of the addition. Okay. So, these are the things you can work out on your own, just putting in all these formulas and doing a little bit of algebra together. Okay. And you come to this final answer. Now, the last part of say making a laser. See, we have studied the absorption and emission process in a lasing medium. We have studied the passage of light through a medium. We have studied what is population inversion and how population inversion is important for lasing action. Then we have studied the 2-level system, 3-level system, 4-level systems. Okay. And we have also studied the broadening. So, you pretty much have all the ingredients, all these ingredients necessary to build a laser. And of course, last but not the least is the optical resonator. And I will be describing this optical resonator in a bit of details. Okay. So, as I have introduced to you before, The optical resonator here, if you look at this diagram, consists of two mirrors, one here and one this side, and there is a lasing medium somewhere in between, and the dashed line in green shows you the axis of the laser. So, these are all different resonators, 1, 2, 3, 4, 5, 6, 7, 8 resonators. Now, what I have shown here is what I mean by modes. So, I have introduced this word modes. So, if you were to see an axial mode, specifically it is called axial mode, you could have a wave which is, which has a frequency like this. It is a standing wave. So, there is a mirror here, there is a mirror here. So, you have this the laser or the laser light or the stimulated emission light, which is bouncing back and forth between these two mirrors, and it forms a standing wave like this. It could also form a standing wave like this, it's within this constraint of the resonator. It could form a standing wave like this too, okay, like this, like this, like this. All these modes are possible, and if you see, these modes are something like a frequency. If you have, this is one wavelength, it is going on this way, it is going on this way. Here, this wavelength is shorter and shorter. This is a very short wavelength. This is the shortest wavelength which I have shown in all these pictures. That means the frequency is higher. So, this frequency is different from this frequency, and all of them are different, okay. And we are going from a lower frequency to a higher frequency. So, modes basically is some kind of a frequency, if you would say, okay. Now, in a resonator, so you have these kind of frequencies which are happening. Now, just turn your attention to this picture here, okay. So, here the x axis is the frequency line, okay, and this gives you the gain medium. Gain medium means the broadening of the grain profile, okay. So, this is my gain profile in that medium, okay, and these lines are the modes, and they are all separated by equal frequency. This mode is separated from this mode by an equal frequency. This mode is separated by this mode by an equal frequency, but they are increasing, say, in this direction, okay. So, this frequency is slightly lower than this one, okay. This one is slightly lower than this, and so it goes on. This way you have an increasing frequency. So, periodically oscillating modes. Now, which frequency will be finally possible in a lasing medium will depend on all the losses. Some of these frequencies may just lose out in the cavity itself. So, you have something like this loss line, which is an imaginary line, okay. It is an imaginary line. So, all these modes, they are all lasing, all are possible. The ones that fall within this gain medium is shown mostly in red and partly these blue ones do not lase at all, because they do not fall within the gain medium, okay. Out of these also, the red ones which fall within the gain medium, that means they can possibly lase. Only those will lase that cross the loss line, okay. So, you see there are two parameters. One is you have all these modes which are possible, they have to fall within the gain profile, and once they fall within the gain profile, they have to cross the loss line. Then only the lasing action can start, okay. So, by the way, these are called longitudinal modes. We will come across some more of these in the coming slides, but just remember, these are axial modes and they are longitudinal modes, and they are a kind of frequency. When I say modes, they are kind of frequency, okay. And actually these modes are spaced out as C by 2L. Okay. This is this delta nu. Okay. So, C is the velocity of light, 2, and L is the length of the resonator. Okay. That means this length, this whole length. So, they are all nicely equally spaced and the spacing is given by this. Okay. Now, let us go to the next one. Okay. So, now I want to go into a little more details of laser beams and resonators. Okay. So, how these laser beams travel in a particular resonator. Okay. That is what I want to describe, okay, to you. So, just see this diagram in the a rectangular piece here. You just focus on this part here. So, and we will be just considering ray optics for the moment. Okay. So, now ray optics is, you are just drawing straight lines. This is the ray of light. Okay. It comes here, and between these two dashed lines are some optical element. It can be a lens, it can be a mirror, or it can be the lasing medium itself, just some optical elements within these two dashed lines. Okay. This is the dashed line and this is the dashed line. Now, we have a ray of light here. This part can be treated as some kind of a black box. So, this ray of light just passes somehow here, and what we want to know is what happens after it comes out of this optical medium or optical say instrument or whatever, it could be a lens, sphere, anything. Okay. So, I have this coming in here. So, and this is the axis along which this ray is passing. Okay. So, now I have to describe what I have as an input parameter is x1, that means the distance from this axis to this point where the ray has entered in the input plane. I want to know what happens to it at the output plane. Okay. So, I have this input parameter, and I also have this angle x1 dash. Either it is the angle or you can call it as tan theta, it could be just tan theta, the angle at which it is with the optical axis, which is shown by the red line. Now, the output is given by x2 here, and it has an angle with this output plane which is given by x2 dash. So, you could write a set of linear equations for x1, x1 dash, x2 and x2 dash and solve the equation. Okay. That is how we go about, A very easy way to do it is if you have studied matrices in mathematics, or you must have in physical mathematics somewhere in some course you must have studied matrices. So, a very easy way of solving this equation is by matrices. Okay. So, here I have a matrix. See, x2, x2 dash, a, b, c, d, x1 and x1 dash. So, this is x2, x2 dash is the output here, that is what I want. And a, b, c, d matrix describes what is between these principal planes, between these dashed lines. Okay. And this is my input. So, x1 is known, x1 dash is known. Basically, this is just another way of writing an equation. Okay. So, x2 is equal to A x1 plus B x1 dash. Okay. So, this is one equation. Now, x2 dash is equal to C x1 plus D x1 dash. Okay. So, the idea of writing this is to just show you this matrix part is like two equations you have and you just solve them together. And if you have a matrix like this, things just become easier. You just have to bother about this part and do all the equation gets solved. So, as an example, matrices for I have just given for 3 optical systems. One is, say, between these two dashed lines, that is these two dashed lines. Okay. I have a medium which has a refractive index n. Okay. Specifically, I take n is equal to 1, it is just air. Okay. You could put something else, some other lasing medium with a different n equal to 1.5 or something like that. But okay, for the moment, just to understand, I will say that you have n. Now, what is the matrix for this optical system? Matrix means I am talking about this ABCD matrix. So, the distance between the planes is d. So, the matrix is given by 1 d by n, 0 and 1. Okay. So, n I can substitute as 1 here. Okay. I just wrote the full thing. Now, the next system is, say, a lens. We come across lenses very often in any optical systems. So, again this red line is the optical axis, same as this optical axis, and we have a lens in between. A lens will have a focal length where it focuses. So, what will be the ABCD matrix of this lens? It is given by 1, 0, minus 1 by f and 1. Okay. So, this is for this. Now, suppose I have a system between these two dashed lines as same a lens here, but it is kept at a distance d. Then the matrix would be 1 d minus 1 by f and 1 minus d by f. So, 1 minus d by f is d, 1 is a, okay, and b is d, and c is minus 1 by f. So, you get the hang of it. Now, like this, you could have a periodic sequence of such elements. You can have one lens, you can have a second lens, then after that you could have a block of glass, something like that. So, there is a periodic sequence. Now, you would like to know x2 and x2 dash after the ray has passed through all this sequence of things. Okay. Now, this is a periodic sequence. Now, this periodic sequence could be stable or unstable. Okay. So, this whole set of optical systems which is falling in the path of this ray and we want to know what is the output, could be a stable system or an unstable system. So, what do I mean by, so here periodic sequence, it could be stable or it could be unstable. Stable means periodically the whole beam gets focused, your ray gets focused. Unstable means there is a hyperbolic function which comes into the picture, more and more dispersed as the rays pass through the sequence. So, as the rays are passing more and more through these elements, it is getting defocused, it gets defocused and it comes out as a very wide beam. Your input beam could have been a very tiny beam, but tiny means in diameter, and output is very large and it just crosses all the elements, you know, the maximum diameter of these elements, it just crosses all that. So, that is not what we want. We are actually, we would like a system which is stable. So, let us see what we can do to make it stable. Okay. Okay. So, here I have shown the periodic sequence and stability of laser resonators. So, this is the periodic sequence A B C D A B C D, you know, you have this some element here, some element here, some optical element here, some optical element here. So, the input is x0, x0 dash, where x0 dash refers to the angle made by the ray with the x axis, x or z or the axis, okay, along which the beam is travelling. Then after this element, it becomes something else, x1 and x1 dash. So, that you can solve by solving the matrix equation. Similarly, then this becomes an input to this set of optical elements, then again you have an output, and so it goes on until, you know, the nth optical element you have crossed, the ray has crossed, and you get xn and xn dash. Okay. Now, these sequences are stable when the trace A plus D follows the inequality -1 is less than half A plus D less than 1. Believe me, this can be derived, but just believe me for the moment that this is the inequality which it has to follow in order to be a stable sequence. Okay. A plus D refers to this A and the D. Okay. A plus D in a matrix, this is the A plus D. Okay. So, once you have this set of matrix here, the relevant set of matrix, you can always add A plus D, do all this, okay. That is what happens. Now, as an example, let us take a sequence of lenses. Okay. So, I have this one lens here with a focal length f1, then I have another lens with a focal length f2, and the dashed line shows the principal planes. So, I have a ray which enters here and something happens to the ray in this between these two planes and then it comes out. So, I want to know what happens to the ray when it has come out, or whether that ray, this system is stable enough or not, whether that ray has diverged completely or it has remained close to this axis shown in red. We would prefer it to be close to this axis, then only it is stable, okay, and it has to follow this criteria. Now, so what do I do? So, I have 2 bits, this is one ABCD matrix I must write for this part, and one more ABCD matrix for this part, okay, and that is what I have written here, 1 D1 minus 1 by F minus 1 by. So, this one refers to this part and this matrix refers to this part. Now, these both have to be tackled together. Okay. So, once you do all this, this bit of algebra and matrix multiplication and all that, you do all that carefully. If you do, you will come to the conclusion, okay, it has a certain matrix element, which let me show in the next slide. I have just done it here. This is matrix multiplication. So, if you have 2 matrices like this and like this, then the matrix multiplication is given by that. So, patiently if you do the matrix multiplication of this, it is one big thing of this kind. Okay. So, this is A, this is B, this is C and this is D. So, for that stability part, all we need is this A and this B, which we have to add up together. Okay. So, I go back to this. So, I do this because you know, why have I taken this example of lens? That is because it actually is very similar to two spherical mirrors which form the resonator of a laser. So, these are two spherical mirrors which form the resonator, okay. And it has a radii of curvature R1 and R2, okay. And F1 is R1 by R2 and F2 is R2 by 2, R1 by 2, F2 is R2 by 2, and the trace is equal to A plus D. So, if you put all these, if you just substitute F1 by R1 by R2, because we are interested in that, finally you will get a condition which is of this kind: 1 minus D by R1 multiplied by 1 minus D by R2 should be greater than 0 and this one should be less than 1. Okay. Then only it is a stable sequence of optical systems, and it will be a stable resonator. Okay. Thank you.